Thanks, Sylvie.
Good morning, everyone. So we have this morning, we put together a panel that's called Demystifying Undersea Cables or Submarine Cables, whichever way you want to call it. So we have Samia Barsoun, who is a cable builder, and we have Paul Kerwin, who's a cable operator and who runs the services on the cables. So what we have put out for you as an agenda is basically we want this to be an education session on submarine systems. So everything you ever wanted to ask about submarine cables, now's the time to ask. So we will start from the beginning. So we'll start from building a cable, how do we build a cable, and then we'll go through all the development process. Who are the key partners in building a cable? What are the typical ownership structures? And also we'll do comparisons on the various ownership structures. As a second part, we'll show you who gets involved into building, how long it takes to build a cable. And after that, we'll go into the service layer, what kind of services you can buy on submarine cables. As you know, the internet is a very large consumer of submarine cables. It is by far the cause of demand for submarine cables, which wasn't the case 10 years ago. So we have with us Samia here. Samia was an engineer at an R&D engineer at Bell Labs, and then she moved to executive functions with P&L accountability. She has expertise in wireline, wireless, terrestrial, subsea, microwave, long-haul, metro, and access systems. She's a real expert in fiber optics. She consulted for Nokia Siemens, Alcatel, AT&T, IDT, Lucent, Tyco, and TeraWorks. She's also an entrepreneur, and she founded her own company, and that company did some fiber optics characterization services called FiberWorks. We have here Paul Kerwin. Paul has 26 years of experience in the telecom industry. Most of that experience is with cable and wireless. He has recently joined Tata Communications. So he has had a wide variety of roles in the carrier business, ranging from customer support, global account management, service management, and commercial and operational management. So we will start now with Samia's presentation, and we will take questions at the end. Unless things are not clear and you're absolutely burning for a question, you can come to the mic, but we would like to have the two presentations first and then entertain questions at the end. Thank you. Samia.
Good morning. The first thing I wanted to clarify about demystifying cables is I prefer to use the word undersea. In 1985, when I started working with Bell Labs and I was telling people, you know, I work on submarine systems, they looked at me and they're like, I wasn't sure whether they were impressed or horrified, but I think they didn't want to bang their national security on me. So let's call it from now on undersea fiber optic cable.
So this map that we are showing is the current map of all the systems that are laid around the planet. The systems that are there are either current or in planning phase. And to be on the map, they had to be announced by December 2007. So this is the latest map.
Okay, I just removed your map, Sylvie. Well, thank you very much anyway for the intro. So the first part of my talk is going to be really a technical overview. I mean, Sylvie mentioned I was a cable builder. More precisely, I'm really a cable designer. I don't want to take responsibility for the fishermen fishing out the cable and breaking it. You can laugh, you know. So these are the parts of a fiber optic undersea fiber optic system. In terms of demystifying, it's really not that complicated. It's a transmission system. And unfortunately, I do not have a pointer, but so I'll walk you through it. At the middle of, between the two shores, the green, of course, are the land sites. And you have what you see, lines. And in the lines, you will see fiber cables, as pointed in. You will see repeaters. And I'll discuss every one of these components through this talk. And you'll have branching units. And then on the terminal equipment, you will have you have all the transponders and everything. And you also have the cable station where it's all included. And, I'll give a talk for about 10, 15 minutes on this. And please, at the end of the talk, any question you have, please feel free to do it. So let's talk about the cable. I mean, it's really from a mechanical perspective, cable design in undersea is very, very impressive mechanical endeavor. And what you see in here, you see at the very thin end of that big cable, you see the fiber. And really the fiber is no thicker than my hair. I mean, not the whole hair, but really one strand of hair. And is about 125 micron in diameter altogether. It's really, really very small. And this is where all your traffic is being carried. And in order to protect that cable, you basically have some steel around it. You have a copper conductor, and one also of the reason of the copper conductor is that also you have to power your electronics in the ocean by sending power through this conductor. And of course, around it you have a polyethylene insulator. And what you see, the last stage of that cable is a steel armor. And you don't always use it when you go into deep, really deep ocean. But as you get closer to the shore and to more challenging territory, you start using the steel armor. And we call it armored cable versus lightweight cable on your right-hand side. This, I would say, is absolutely the most impressive piece of equipment in the undersea cable systems. Impressive, why? Because your entire design, the entire design of any system you have out there and the progression of cable system and their capacity resides in the design of that element here. Not only from the physical standpoint, because it has to withstand depths. The deployment can go up to 8,000 meters in depth. Can you imagine the amount of water pressure on that? And they call it a repeater. And its function, its primary function, is to amplify your signal. As you send the signal from the shore end, and it travels through the cable has some attenuation, and you get into that repeater, and it amplifies it, as shown in the little diagram here, and then it sends it out to the next repeater. Now, the reason I'm saying this is a really challenging part, look at the big box down here. It says 4 amplifier pair repeater. What that means is that you have 4 pair of fibers coming into that repeater. And today's repeater can take up to 8 pairs of fibers. But even more important is each of these boxes here on top, as you see, it's like you have this, hexagon, and each one of them carries an amplifier pair. But if I were to take you back about 10 years, in the early 1990s, when I started working at the labs, actually in 1985, we were working on TAT8. And TAT8 was a regenerative system, meaning every one of these boxes, instead of having an optical amplifier, had almost what you would see today as the electronics, the high-speed circuitry in the terminal equipment. So every time you change your terminal equipment, you needed to change that repeater. However, with optical amplifier technology, and you've heard the words DWDM, I'll go through a slide to explain to you a little bit what it is. But through optical amplifier technology, you're able to keep that repeater in the water and add capacity on demand. And the optical amplifier itself is bitrate and format independent. Unfortunately, you cannot always have your cake and eat it too. There are impairments, and a lot of the design of that cable system has to take place in that space. And later on I'll talk a little bit about the commercial aspect, but some of the surge in capacity, and if you notice that capacity has become cheaper and cheaper, is precisely because of that invention, the optical amplifier. What you have also, if you look at the upper right-hand corner here on the slide, what you have is a branching unit. So why do we really need branching units? So imagine if you wanted to carry traffic from one side of the ocean to the other side of the ocean, and then you wanted to carry traffic from that same side of the ocean to another part of the continent. You would need really two cable systems, right? If you didn't have a branching unit. Within the branching unit as well, you could have it as a passive branching unit. It should just take your signal and split it off, but also it could be an active branching unit. And the challenges of this branching unit are that you also have to power them. Then we go to the cable systems. Now we're getting submerged. As we submerge ourselves and we go into the shore, you basically what you do, look at this picture. Whoops, it wasn't captured here, so I apologize. So basically what you do, you come in from the sea and you drag your cable in and you trench it and you basically terminate your cable into a terminal office. And this is where your entire traffic is happening. And Paul, I believe later when he's going to talk about services, as you know, it's interesting because there is an evolution in this whole thing. Is the cable station were exactly near the shore because it really costs a lot of money to actually trench the cable, terminate it. At that point, you're actually getting some armoring in the cable. But today, because of the technology, because of the lower losses in fiber, because of the tremendous amount of capacity that you can actually put on those cables, the cable station is more or less remotely located from the beach. And then you can start blending your services in. So let's see what's in that cable station. As I mentioned, you have all your terminal equipment in there. So the first element, which really, it's an expensive piece of network equipment, is at the bottom here in the middle. It says PFE, is a power feed equipment. You do not have the luxury undersea to just plug in your power system in some place. And basically balancing the power budget, actually how you power the system, is very, very challenging. It's not just, back of the envelope electronics. Mathematics. Above it, you see a line monitoring equipment. Okay, some of you are like, oh, what's happening when the cable gets cut and everything. Where that piece of equipment, which is sitting in the cable station, thousands of kilometers away, from that one repeater, 8,000 kilometers down at the bottom of the ocean, is able to tell you at any time what is the quality of your system. And also, if you have a fiber break, can you imagine, and you guys have experienced it, during the Taiwan earthquake and other fiber breaks that has happened, but can you imagine if you needed to actually go search that ocean for the repeater that failed, unless you had this line monitoring equipment? And again, the technology that went into it, Tyco, for example, uses a high-loss loopback. They put kind of a bridge, and it requires quite a bit of system and data analysis to identify the right cable cut. Alcatel-Lucent, I believe they use a supervisory channel, transmit and receive, and then they send signal to the repeaters. But bottom line is that you can within, I would say right now, in some instances, you can within hundreds of meters really locate the cable cut, thanks to this piece of equipment. And it has evolved over the years also. Also, from a monitoring perspective, in your left-hand corner, You see that little computer, your craft terminal interface is your element management system. So when you terminate the cable in some little hut, you have, maybe just a craft interface that talks remotely to the system. But that piece of equipment and all the software behind it will really provide you with network management of this entire network and some supervisory. But last but not least, you see on the right-hand corner here a really tall piece of equipment. This is what you call the high performance. This is the terminal equipment. This is where your data is generated, sent into the ocean, and regenerated at the end. So I'm going to focus on that because, again, from a design perspective, when we talk about DWDM and wavelength division multiplexing, this is where the design has gone into. So far, so good? We call it a hippo, not really for hippopotamus, although we've been trying to tell Tycho to change that particular name. But it's really a terminal equipment. So what you have in here, you have, how you see 1, 2, and minus whatever. What you have, these are channels. These are wavelengths. What a wavelength is, and I apologize for those of you who really know the optical field, but I'll go back into the, the details here. What a wavelength is a color of light. It's simply a color of light. So what happened is that you take optical signals of different colors of light, and you combine them, you just combine them into this, what we call this WTE, which is a wavelength terminating equipment. So once you combine them all together, you're like, oh my God, they're going to be all mixed up and all, well, the beauty of photons is that it's a gross simplification, but they really don't interact. Every color of lights is going to stay in that, where it needs to be. But of course, as I mentioned, cable has loss. And you need to actually transmit over thousands of kilometers. So what do? Even at the terminal station, you first amplify it. Even when you go through the WTE, you kind of lose power per channel, right? You're combining. So the TLA is a transmit line amplifier. In reality, it's just another name for an optical amplifier. What it does, it takes all these wavelengths, and I believe today, we can transmit up to 96 wavelengths at 10 gigabit. This is where the word terabits of terabits of capacity is coming from. So you can package them so well because this optical amplifier is fabulous. It really takes anything in that wavelength range, which is in the 1.5 micron or 1550 nanometer spectrum, and it amplifies it. But the trick is, so that was interesting. When I was in research actually at Bell Labs a few years ago, that was about 1990, 1991. When we discovered optical amplifiers, there was a lot of resistance. Oh, this is new, and this, We found out they were really a very clean instrument. They do not introduce too much noise. And we told ourselves, oh, great. We're going to put one channel, it's going to get amplified. We put 10, they'll get all amplified equally. Well, as we all know, we're not all created equal, although we really like to think so. What happened is that the optical amplifier on its own has a profile. It has an amplification profile. And what you see in here, it favors some wavelengths over others. So just imagine, I've just taken some wavelengths, so many colors of light. Each of them are carrying 10 gigabit of capacity. I take them through that amplifier, and guess what happened? The middle one gets really strong. This is a Darwinist law of optical amplifier. And the one at the edge kind of are left behind. But thank God, we have very good scientists out there that figured out a way to cheat the system. So here I put the repeaters. So every one of them, by the way, every TLA, every optical amplifier is one of those boxes here. I just wanted to put it here in perspective. So what do we do? There is an element I didn't show you in the first view graph. It's called a gain equalizer. It's that little box in red. Looks like a repeater. It's boxed into a repeater shell. You know, we use a sim mechanical design, but it's a gain equalizer. So it looks like that. And what it does exactly what I told you earlier. It equalizes the gain. So what we do, the wavelengths that are a little bit less favored, we give them a head start. At the shore, what is called is a concept of pre-emphasis. Then it goes through your chain, and the wavelengths at the middle are catching up because the amplifiers and the repeaters are favoring them. And then you have this gain equalizer, which is placed not only in one spot, I mean, sometimes there are more than one in the system, and it basically equalizes your channels, and it gets transmitted. It levels off the playing field, really. So now we have all the elements. We have the terminal equipment, which is dense wavelength division multiplexing with multiple channel of light getting transmitted. We have the repeaters, which are optically, which are really optical amplifiers. We have the gain equalizers. We have the power feed equipment. You have the branching unit. You take all this equipment together. What do you do with it? Basically, you could configure it depending on your geographical limits. So in transoceanic network, what you see on your left-hand side here, you have what we call a trunk and branch system. One thing about engineers, they're really good with equations. They're not very creative with names. So what we do is like, you take this whole optically amplified system, you go into a branching unit, and you go inland. And as you see, even the branches are on their own a repeated system. To the right side of that diagram, you have what we call the coastal network. So here you are, for example, on the east coast of the United States, and then instead of putting terrestrial cables, when you're paying $100,000 per cable kilometer, you may consider going a little bit in deep waters. So you go from city to city, and what you do the same thing. It's a repeated system. You have a branching unit, and sometimes from the branch, and this is again, it's really tricky. You really have to understand, you have to survey the ocean, and I'll talk about it later. There are a lot of people that get involved in the design of this thing. And really what happens is that you basically can trunk and branch them. And then what we have is repeaterless system. Yes, they're out there and they're great at times. Why are they great? Because they don't require repeaters. So if you don't have any repeaters, you have nothing to power. So you don't need any power feed equipment. Not only that, you don't need, the cable, it depends. Cable is the same. Sometimes it's a thin cable if it is in deep water. But often you have a lot of armor cable because they're really in inter-island and you're getting into rocky situation. So you have this point-to-point repeated system. And you could also have coastal networks that are short in distances that are also repeaterless network. So it's up to the designer, once somebody comes with a demand and say, this is what I want, it's up to the designer to really make sure that they design the right system. It's a lot cheaper, many, many times, to have a repeaterless system than to have a repeated system. But of course, you can go across the ocean with it. So the total transmission lengths for a repeated system, I said unlimited. This is like really wishful, but right now I think it's 11,000 kilometer, the longest system. 11,000 kilometer. That's a lot of kilometers. The non-repeated is 400 kilometer. A few years ago, we could barely do, I'm talking 6-7 years ago, not even. You could barely do 250 kilometers. There are new amplification method called Raman amplifier where actually people are using the fiber itself, the fiber, to act like an amplification medium. is fascinating. Electrical power, as I mentioned, there is no powering. The maximum number of fiber pairs in the cable is 8 in the repeated, is 12 in the non-repeated. And branching units, it depends. You have mostly passive branching units. And right now, there is a new type of branching unit. It's called an optical add-drop multiplexer, and I won't even go in detail. It's just another way to saying you're splitting the signals and you're rerouting them and keeping the wavelength's integrity. And the maintenance, complex, simple, obviously when you have a long repeated system with all the elements in it and in depth, in water depths, is a lot more complex. And the cost, obviously, you're paying, I think the average is about 30 to 35,000 to maybe 30 to 40K, I don't want to quote anybody here, per cable kilometer for a repeated system. Is a lot cheaper for a repeated one. And I won't quote it because I'll get nailed by the vendors. So, primary cost of system in construction. How much do they cost? So you have the network construction. The wet equipment is everything in the water, obviously. The dry equipment is a cable station and everything in the cable station. You have installation and testing. You have project management. You have terminal station building. And it's shore property. And if you've worked the real estate lately, you're paying a lot of money for shore property. Everywhere, even in New Jersey. Project startup, you have licensing and permits. You have the legal, you know, you have to hire the lawyers. I don't know if any of you had to deal with lawyers, but I promise you they're not cheap. And you have obviously people in the financial industry. The access cost is backhaul. As I mentioned, you have to dig through land, and the capacity cost. And then you have the operation and maintenance cost. And those are really not only during the construction of the cable, but they will be your biggest cost after the cable is built and installed. And how much do they cost? They cost anywhere between tens of millions of dollars to hundreds of millions of dollars. I'm talking 300, 400, $500 million cables. And if you look at the breakdown, and this is a beauty, and here in this histogram here, what you see that the first upfront cost, when you go out there and install a system, your first cost is a cost of your wet plant. The repeaters, the cable, all that stuff. Then, and why is your dry plant cost so cheap, relatively speaking? Because you're not loading the system completely. You're just putting what you need. But as you go further and further and implement, your dry cost becomes an increased number of wavelengths for your system. Your dry cost, your terminal equipment begins to take over the cost of your entire system. And it's really a balancing act. How much capacity? How much are you willing to pay? And what is it that you need? So I just mentioned this. It's like really cost tens of millions of dollars to hundreds. It takes 12 months to 24 months, and even more so for really big system to put them together. And it provides, I mean, I talk about terabits. Terabits is 1 trillion bits of information on one cable. It's amazing. You know, a few years ago, it was like 300 voice calls. You should like that, the ISP providers. And it provides high quality transport, irrespective of how many cable, you know, we always remember the bad stuff that happens to us, but you couldn't get today. Those components, those repeaters are designed for 25-year life and more. They're underwater. I mean, really, when you get the cable break is when procedures haven't been followed. When you have a cable sheet coming in, nobody's monitoring the area, and boom, they grab the cable and take it out. Or sometimes you have some shunt failure. You know, in some cases, if the cable is hanging, you have some sharks that get attracted to like some of the electromagnetic field in the cable and come and bite it. So it's pretty cool. Bell Lab had hired like a lot of biologists at some point in time to look at this. So really, and then the next part of this, so in summary, really, you're looking at something that is extremely, extremely reliable and very high capacity transport network. So thank you. This completes.
Yeah, go.
So should I ask for a question now?
No, I think you should continue.
Yeah, how much more time do I have for the rest of it?
6 minutes, and then it's
Oh, 6 minutes, then that's great, because I won't bore you with commercial stuff. I heard you're a technical group. So I'll go really quickly through this. Okay, here is 3,000 kilometer cable. Implementation in about 24 months. So look at all the activities that take place pre-contract. You have to plan, procure, develop, and then you send a request for a proposal. Usually, when you're actually going through the pre-phase activities, people call, ask for ROM, rough order of magnitudes. And I remember our clients hated them, because you would give them a ROM estimate, and all of a sudden you come down millions of dollars cheaper. And they're like, what happened? Oh, maybe if I wait a little bit longer, you'll drop the price. It's not really the case. Once a client is really committed to building a cable, once a company is really committed to put a cable in place, then there are a lot of activities, like the desktop surveys. Those cost a lot of money. So we don't go into real details on these projects until there is a seriousness from the part of the client. And then you go all the way, you do the detailed design, and then you commit the manufacturing. Because some of these repeaters used to cost us $1 million a piece. It's cheaper now, but they were that expensive. So you do not commit manufacturing until you're sure somebody wants it, and it's designed for that particular system. And then installation, you have to book, and then, of course, once you commission the cable, you have the operations and maintenance. So I won't go through this. So you have a pre-contract. Who gets involved? Everybody. This is worse than the United Nations. The telecom carriers, the private investors, the government ministries. I'm not kidding. If you could actually get a cable done together, you could really run for office. And I'm really serious about this. Then you have the lenders, the money guys, and then the regulators. Everybody wants a piece. Oh, why, how much? And really people who are not all understanding the technology. Then you have, of course, the environmental agencies. I really have to, I'll take 1 minute for this one. We're putting a cable, this is a land cable in San Francisco, in the area, Point Arena to San Francisco. First optically amplified DWDM system in the world. You have no clue how much we had to explain to the environmentalist that this is really a harmless piece of equipment. Really, it's amazing. But you have to maintain those standards. And thank God for them too. And then you have the turnkey suppliers, you have maintenance administration, and of course you have people like me who want to get paid all the time, and we're called the consultants. And then you have the lawyers. And those are terms, you have the presentation. Those are terms that you encounter, MOU, Memorandum of Understanding, demand forecast, all this, this is jargon in our industry. So if somebody walks up to you, MOU is not MOU, it's really Memorandum of Understanding. And ITP, which is really the favorite place where, it's called an intent to proceed. This is when you go out and celebrate. Okay, I'll give you really 3 more minutes for this. How do you procure them? It used to be, you have 3 types of procurement. Traditional consortium, private ownership, and hybrids. Not the hybrid that you see in your gaming, because I see this is a really young crowd. So it's really hybrid joined between the two. Traditional carrier consortium, a typical system is IMEWE for a traditional system, is joint development by carriers and owner who share the facility. People often say that the undersea cable business is really incestuous. It's like a big family. It is really true. By the time it takes to design a cable, do a cable, everybody works together. And the carriers are your AT&T, your Verizon, your Sprint, your BT, your Tata Communications. All these carriers are really, participate, and you have consortium cable, and they sit around tables, and they're like the government sometimes. They take all their time. They like to wine and dine, and, and they talk about how to build the next best cable. And they take the requirement from you guys, the ISPs. who are generating, you know, the growth in demand. The private networks. This is interesting. I worked on the, well, before Global Crossing became Global Crossing, I negotiated, I had taken my R&D hat off and I became a commercial person. And it was very interesting. It was the first, it wasn't the first private company, but you know, when they did the Atlantic crossing, I really had a good feel what it takes to do these cables. I mean, these guys came up with $400 million. Just like that, investors. And they said, we want to put a transatlantic cable, Atlantic Crossing 1 at the time. And now you have a lot of companies, you know, that are coming on, you know, like VSNL, now Tata, and, you know, TGN has built their own private networks. But the way, actually I want to go back to this one, the way on traditional owners sell capacity, because this is what you guys are using and are buying to transport your internet stuff, is sold by individual owners. You have people that call you and they say, you know, they sell you capacity on those networks to the carriers. The private network, they sell IRUs, which are irreversible right of usage. You own it for like 25 years. And they also can lease it. And they have published pricing. And sometimes those guys are really limited by the market. In traditional system, they decide, it costs us so much, we're going to sell you that for that much. The private networks came in very competitively and they said, okay, this is a market demand and I'll sell you an ST, and this is why the price of capacity had dropped tremendously in the rough times. And then you have the hybrid network. It's really nowadays, because what we're finding out, you need both worlds. You need the private investors fronting a little bit the capital, and also you need the carrier networks that are coming in and really building these. And the capacity pricing, it could be like the consortium, but it also determined by market condition. So you have a mixture of both. Thank you.
Cassandra. We'll now...
No time for questions?
We'll do after.
Okay,
Yes.
very good. Yeah.
We'll take the questions after for all parts. Now we'll move with Paul, and Paul will give us an idea of how these cables are dropped in the ocean and what can happen to them when everything goes well and when everything fails. And also he will give you a good overview of what are the services, excuse me, what services are offered on cable systems.
No, I think you need to get out.
I should have had that to keep people on time.
Good morning, everybody. Samir did a wonderful job, though. She actually stole some of my thunder, so you'll see some repetition, I'm afraid. But thank you for having me here. Most of my esteemed colleagues in the cable industry, submarine industry, and capacity are actually in a conference, a similar conference down in Washington this week, International Telecoms Week. So for your sins, you've got me, the poor substitute. But I've been around cable systems for a very long time. Been around cable operators, cable depots, you name it. There's an awful lot goes into submarine systems, as you just saw. And I've also been in the IP and ISP environment, and certainly a lot of folks seem, you know, it looks like, it feels like, and it is magic. And it certainly takes an awful lot to deliver the tranches of capacity that we need in the industry today. And when Samir talks about network upgrades and putting more terminal equipment in place, we're talking in tranches of 320 gigabits at a time. So it's a significant investment for all of the cable operators to go through the user groups, the forecasts and the demands, to be able to go back to investors or go back to the capital reserves and put more equipment on the submarine cables that are already laid. So I'll just go through a quick agenda. Again, I think you've just heard a very elaborate description of cable systems, so some of this will be a little repetitive. the fiber optics, the landing stations, what segments are, repeaters, cable laying, cable faults. I think you'll be interested in cable faults in particular because quite a lot of you thought there was quite a lot of blogging and conspiracy theory going on around the Middle East earlier this year, and Flag Reliance have found satellite pictures of two ships that they suspect did all the damage to the cables, so they are going after them for insurance. I'll go through some of the products and services. I'll also talk a little bit about backhaul and terrestrial because, as Samir talked about some of the cable systems and whether they're private or consortia or hybrid, it actually has some bearing on who can provide backhaul services to those cables. We'll look ahead and see what cables we're primarily involved in, but also what the industry's involved in. So, fiber optics. You've just seen a couple of photographs. The repeater going into the sea there on the left-hand side. The repeaters, again, they are a remarkable piece of equipment. When you think that they've got to be fault-free for 25 years sitting at the bottom of the ocean, they are probably the most elaborate and substantial piece of the cable system. And again, another depiction of a branching unit. The branching units become probably the most costly. They're also becoming the most strategic point because you'll see that many cable systems are running long lengths. For example, South Africa to the Middle East, up the East Coast, and yet not all the countries have bought in. Nobody knows what's going to happen with competition on the east coast of Africa. So they strategically often design branching units into the cable ready for the ability to put another landing into a country. So they're not only useful at the early stage of a life of a cable, but also throughout the life of a cable. And we're actually just doing a piece of work between Guam and Tokyo, and you'll see the cable system that we're going to bridge into that. But we're actually going to take down the cable and insert a branching unit. So again, a change on the normal cable design where you're actually going back and you're looking at the design and what can it take, how many fiber pairs can you divert, and so on. There's the typical fiber optic cable, as you saw. I do have an example here, so if nobody's ever seen one. You may have all seen the fancy little insert, which is the very small inner section of a cable. This is actually a piece of recovered cable from the Caribbean, which has obviously got a bend that is far greater than the normal radius that fiber optics can handle. So you're welcome to have a look at that. And I thank one of my colleagues bringing it from Miami to Washington over the weekend. He got some odd looks when he went through the airport. Cable landing station. This is our cable landing station in Wall, New Jersey. You will find that most of the cable systems, for obvious reasons, the cable landings are very nondescript buildings. It houses the generation. Most of them have got dual power supply from the local utility. They then have multiple diesel generators, just like a normal data center would have. Obviously, very stringent AC and DC UPS systems. The main thing also, which Samir didn't mention, on the PFEs, it's, depending on the length of the cable, again, the power equipment is one step ahead again because it's constant current, and when constant current, I'm talking correct me if I'm wrong, but 7,200 milliamps plus or minus 1 milliamp. It has to be absolutely perfectly clean, and we're talking thousands of volts DC, 7,200 milliamps, and constantly fed and very, very clean. The cable laying. I think many of you, if anybody's on the East Coast, if you drive up by Baltimore, you'll see the Tycom cable ships just after the bridge on the right-hand side, a couple of gray-looking Dower ships. There are probably 12 companies worldwide that house their cable ships, and they strategically place them across the globe, whether it's Baltimore, New Jersey, Southampton, Bermuda, Viga in Spain, and then you go out all across the Pacific. And basically they're all located primarily down to the maintenance agreements that they're covering. So there's an Atlantic Cable Maintenance Agreement which covers multiple cables. There are privately, there's Global Marine that does global crossing cables and so on. But in the main, they're strategically placed to get to the faults as quickly as possible. The cable depots have to house multiple cable systems, multiple lengths of fiber, different repeaters. And so when you hear somebody say it's going to take 3 weeks to fix a fault, it's primarily mobilization of ships, getting them to the right place, getting them to the right depot for the cable system, getting them out into the ocean, and quite frequently, you know, the middle of the Atlantic, even just 20, 30 miles offshore, off the UK coast or off Brittany and France. It's pretty horrendous weather most of the time when they're out at sea. So when I say specialist ships, these ships can move at 1 knot in very, very heavy seas in any direction. So, you know, they are looking to, when they're laying the cable, they have to follow very, very precise oceanographic surveys. When they're actually looking for the cable, they're using very rudimentary methods, grapnel just to pick it up, you know, find it, tension meters to determine whether they've got a rock or whether they've got a cable, or whether they've got an abandoned fishing net. So, you know, it's a very rudimentary approach, but it's a very, on a high-tech system. The ROVs can go down to 2,500 meters, and they can do some of the search and recovery. As I said, several key players, about 12 companies, Global Marine, Alcatel, Tycom, NTT, and some specialist companies with specialist type ships for inland repair and inland laying. The ROV and the trenching machines, as Samir mentioned, many of the cables over the last sort of 20 years have been buried as close as possible to shore, and also where the environmentalists will allow you to trench. One of the biggest issues is dragging anchors, and you'll find that prior to that, with the old coaxial cables and some of the early fiber optics, they were basically just laid on the sand. And obviously that caused an awful lot of cable cuts. Again, we're looking at the burying of them. The armored cable that I showed you is probably suitable for depths up to about 1,000 meters. As you get closer and closer to shore, the armoring becomes thicker and thicker, and ultimately you end up with steel casing. And the casing is basically interlocked and around that sort of diameter. I couldn't carry an example, it's very, very heavy. But certainly the armoring and trenching is what prevents many of the cable cuts close to shore. And again, the ROVs are used for inspecting the terrain on the geographical survey or the oceanographic survey before they lay it, and then after they've laid it, they go back out and make sure it's in the right spot and there are no crossings. And there are, notably, there are a lot of cable crossings, as you'll see from some of the maps, but most of the crossings and exactly where they are on the ocean floor is known, and that becomes very important as they go out and they look to trawl and pick up those cables when they need to repair them. So cable faults. You probably heard the term shunt fault. Jolt is not often used, but basically what I showed you is external aggression where the cable's been bent, and I'll show you a couple of examples. And again, it's down to the attenuation. The cable may not be broken, but the actual system is impaired. And then it takes all of the planning to take that system out of service, go and find the cable, and pull it up and repair it. Same thing with the shunt fault. Shunt fault is typically an anchor has caused it, where it hasn't actually cut the cable, but it's eaten through the cable into the copper core, and you're starting to get a ground from the power system. And that usually causes one end of the power system to have to close down. so you don't get any damage to your power generation equipment. And in some systems, the Trans-Pacific, for example, they have to be dual end fed. Because of the distance, you have to feed it from both cable stations. Some shorter systems, you can get away with single end feeding a cable, but shunt fault is probably the most common. And again, traffic will often be impaired. There's a danger to the system, and you have to make arrangements to reroute traffic and repair the cable. And then obviously a cable break is immediate restoration. And then the activities around the planning of restoration, there are terms that you may hear from carriers from time to time. The cable administrator is in a consortium, is a designated party who manages all the capacity for all the owners of the system, where it goes, which fiber pair it goes on, or which equipment it's placed on, and they then do all of the administration of the cable system and traffic rerouting. And you'll see RCO and RLO. RCO is the restoration coordinator, and RLO is the restoration liaison officer. Two different functions. The liaison officer is the guy who's dealing with the ships, and the commercial, coordination is dealing with all the owners of the capacity. So here's an example of a jolt, where you can see it's almost like a kink in a hose pipe, but it's enough to cause attenuation on the fiber and a repair after a period of time. Here's a more severe jolt, almost like the one down here, and you can see the armoring is starting to get damaged, and again needs a repair. This is a cable break, where we found one end of the cable but not the other. And he's basically using the techniques that Samir mentioned. You go, you pick up one end, you bring it to the surface, buoy it off, and then you go and look for the other end, bring it up, buoy it off, splice a piece in between, and throw it back overboard. All sounds very simple, but once it's on the deck of a cable ship, as I just showed you, you get into X-ray machines because of the pressure of the joint. The joint is a regular fiber joint, as if it was in the street or in the office, but it has to be done in very, very clean conditions, in a very, very unclean environment on the back of a ship, and then it has to be pressure treated and sealed, and just the very minutest of cavities or gaps, and they have to start all over again. So it becomes a very high-tech environment on the deck of the ship. This is an example of a cable break where all of the armor has been completely lost. And here's where you've got evidence of a fishing net. So you know exactly where the culprit is. This is one that came up earlier this year in Western Europe. So I think, as we've mentioned, the main culprits are trawling in less than 1,000 meters, and ships dragging anchor. The Seamewe 4 and the Flag Fault were reported to be one ship dragging across a length of about 4 kilometers. And it was refused entry into port in very heavy seas, and put its anchor down and dragged it right across 2 cables. I talked a little bit about backhaul systems. We always think it's going to happen to somebody else. And we had the Taiwanese earthquake, which resulted in 22 earthquakes. 22 cable breaks. And we've also had, down in the Caribbean, one of the hurricanes took out a landing station entirely. It was far too close to the beach. This example here is one of our cable systems, and this is actually closer to home. It's in Oregon. It's one of the backhaul sections from Nadona Beach into Portland, and it runs through beautiful countryside, but as you can see, we had many mudslides, and we're talking probably three years in total to repair this, because as you can see, it's along the railroad track, and they have to fix the railroad first before we can actually relay a cable along those rights of way. So that's really, it's quite dramatic. As you can see, there were multiple segments. So when it comes to your planning, it's very important that backhaul is also considered. It's not just the cable landing. If we talk about the different types of systems, if it's a consortia system, usually the owners of the initial capacity and the funders of the cable, the likes of AT&T, ourselves in India, the likes of BT, Verizon, they will normally be the primary backhaul providers. So they will bring the capacity back to a city, New York or Washington. In a privately owned system, if you buy into buy capacity in 10G increments on the system, you can actually build into the cable system yourself. And as you can see, if you put all your eggs in one basket on one route, then this sort of thing can happen. It can take a very long time to recover. We actually have 2 routes back from the cable landing station in Nadona, so we've been able to overbuild on the second route to restore traffic. But it does cause some significant delay in bringing up capacity again. All of these are examples of Oregon. The one on the bottom right is where very, very heavy seas have actually uncovered the armored cable at the beachhead. So again, it just goes to, this one didn't actually result in a cable problem. It's a little hard to see, but you can see the pipe work surrounding it. And again, the power of the ocean on the shoreline is quite incredible. So hence the need to do the trenching. Get to products and services that run over the cable systems. IRUs, indefeasible right of usage. Whoever came up with that name, I don't know, but it's about 30, 40 years old. Usually 15 years. You buy a circuit for 15 years. It's prepaid. You pay operations and maintenance charges based upon your proportion of ownership in the cable. So, you know, quite straightforward. If an annual maintenance charge is $1 million, then you got 10% of the cable, you pay 10%. So the key is that the owner of the capacity takes the risk and the reward. And this is one of the things people will bandy around IRU as a term. But by buying into it, if the cable breaks, the cable breaks. There's no recourse on the owner. The other issue with IRUs is they're supposed to be between 2 fixed points. So you're buying it from New York to London. You're not buying it from London to Washington or New York to Paris. You can't change your mind halfway through. So these are the key elements of IRUs. And you know, there are what I would term enterprise customers and ISPs who are buying IRUs because they do lower the cost of ownership and they do fit into certain business models. But key is that the risk and reward transfers with you, and there's no real SLA. If the cable's down for 3 weeks, it's down for 3 weeks. MIUs is another term, minimum investment unit. In probably 1990, E1 was a minimum investment unit, and that carried on probably for about 15 years. In the late 90s, STM1 started to be the minimum investment unit, and that's 63 E1s. And subsequent systems from 98 with AC1, Yellow, Gemini, STM4, STM16 started to become more prevalent. At that time in the late 90s, the systems were limited to 2.5G capability and multiple 2.5s, and as you have heard now, it's multiple 10Gs in tranches of up to 80, 96 on a fiber pair. So the minimum investment unit now is typically STM16 or 10G. The other services obviously are lease services. I think you'll all have heard the term IPLC, International Private Leased Circuit. Managed private lines, IPLCs I'll talk a little bit more about in a second. Managed private lines tend to be an owner who has managed to secure licenses in different countries, buys the underlying capacity, builds the POPs in the different countries, and manages the service provided to the customer on an end-to-end basis. Capital leases, another obviously example where you're prepaying for a 5-year term and obviously getting a discount and for term and for bulk buying. DS0 to 10 gigabits. So a least circuit could be 64 kilobits, which is a 30th of an E1, or it could be all the way up to a 10 gigabit wavelength, or even an STM64 protected, which would be two 10Gs put into transmission equipment for protection. Ethernet private line becoming very, very prevalent these days. Not necessarily eating into the higher end of the lease market, but certainly starting to eat into frame ATM, and also as an alternative to MPLS, layer 2 and layer 3 MPLS services. And Ethernet is becoming much more prevalent. Still a challenge on the varieties of local access flavors that we have that you can buy, whether it's contended, uncontended, Ethernet access, and so on. But a very, very fast-growing segment. VPLS, virtual private line, running over layer 3 MPLS services. I'm sure you're all familiar with that and running it on your own networks. Again, unprotected wavelengths, which is the core fundamental of all of our cable systems these days. Again, unprotected carries a high risk in that your cable, if it's unprotected, it could be down for a number of weeks. So it's very, very important in that respect to buy on protected or resilient or diverse systems. And the other thing that is probably more pertinent to you is at the moment we can, most cable systems can now do 10 gigabit Ethernet and map it onto SDH and SONET equipment, but also most of them have got the LAN-PHY capability either launched or coming out. So that actually lowers your cost of optics significantly when you start to be able to get those services from the carriers. The most common IPL service, again, the carriers providing the end-to-end service in a managed private line. All protection schemes are possible, and it's always available on all the primary routes in the network. IPLCs have been a mainstay of data revenue for carriers for probably nigh on 30 years, and managed private lines, Ethernet, as I say, is ramping up and taking over from some of the E1s and DS3 private lines that we see. It's common on most of the consortia cables where one carrier provides half the capacity. For example, an AT&T would contract with you. If it's a circuit to India, then as we are one of the regulated carriers and licensed carriers in India, we would provide the other half. There's a permutation of contracts whether the situation is you have to sign a contract in both countries. So your legal entity in India would have to sign a contract with Tata, legal entity in the US would have to sign a contract with AT&T, but then you have a permutations on, do you want single end billing, single end fault reporting, and that coordination goes on behind the scenes by the carriers. It's a very labor intensive process for carriers to continue to work this way, especially as many carriers are getting licenses in most of the countries and can provide end-to-end service themselves. And why share the profits, and why share the revenue with the other carriers? So this is really phasing out. Half circuits are phasing out. There's still many of them out there, but it tends to be DS0s, sub T1, sub E1 type of IPLs. Unprotected service is typical in that if you have designated an IPLC on a particular cable path, there is no automatic restoration. You typically will pay a premium for automatic restoration. For example, CME4 going down, only certain bearers have been designated as automatically protected on CME3, and in the situation that we all ran into where some restoration have been procured on flag. So CME4 goes down, flag goes down, there's no third option. So restoration, as it says, may be available via the consortium. An alternate cable may be available via consortium, but when you're buying an IPLC, it's absolutely critical you understand what restoration is provided. Protection, auto auto protection, service provision with unprotected two-fiber handoff. Typically, most ISPs only want two-fiber handoff. They don't have transmission equipment, they only have a router, they don't have 1+1 protection. You're buying unrestored routes from multiple operators. So this is typically what we would supply to ISPs, whereas 4-fiber would be if a carrier is buying an STM16 to set up his own network, or a large enterprise is putting some optical switching in place where they want 1+1 protection and expect us to provide the underlying route protection. Restored service, again, manually restored. It can take anywhere from, once a cable break is suspected and traffic has to be moved, as we talked about earlier, the restoration coordination kicks in, the RLO kicks in, and this is where you have predetermined plans in place between carriers as to which system you're going to use, and then you start to implement your restoration plan by meeting that carrier at various alternate points, various alternate cable systems. So this is again very manually coordinated with phone calls between NOCs and reading up on plans and implementing switches in the network, and it can take anywhere from 30 minutes to 4 hours. With consortium arranged, when they're moving massive amounts of traffic, it can take up to 15 hours. Again, unprotected service, unprotected handoff to you, the customer, and also if the cable system goes down and you bought unprotected, you're down for the length of the cable repair. Service level agreements, I think everybody will be fairly familiar. These are basic level service level agreements. Premium protected service, anywhere from 5 minutes to 4 hours. You get a percentage based on your monthly recurring charges, percentage credit, and increments from that point on. And as you can see, with when it gets into subsequent 24-hour periods, that is a very challenging situation for a carrier when a customer's bought premium protected and they're down for longer than 24 hours. Same thing, premium protected could be a mesh protection. For example, across the Atlantic, where there are probably 7 different cable systems, and carriers build diversity and capacity on each of them, they can employ optical switching where you could have 1 for N protection rather than your traditional SONET or SDH where it's 1+1 protection. Protected is your typical 1+1, and unprotected, as you say, no credit for almost 4 hours, and above 4 hours you start to get into meteor credits and rebates. Talking a little bit about network operators, consortium examples are all cables you're familiar with. You'll have heard the names: TAP14, CMUV4, Japan, US, APCN2 around the Asian region, and then wholly owned, which has been has grown. This sector has grown significantly in the last 10 years with Tata, which some of you may know. The Tata Group bought the Tyco Global Network about 3-4 years ago. The intra-Asia cable, which we're building, Tata Indicom is India to Singapore. Apollo is UK and France to New Jersey and Long Island. 2 separate fiber systems, 2 separate fiber lays joined together as one system. Hibernia is from Southport in north of Liverpool and Dublin across to Halifax and Lymm. 360 Americas is New Jersey, Bermuda to Brazil. Global Crossing have multiple cables in Mid-Atlantic, South Atlantic, and across the Pacific, and also down into South America. Flag, Reliance Globalcom, many systems throughout the Mediterranean into the Middle East and around into Asia. Gemini, Bermuda and Hugo, and Columbus Networks, which is the example I gave you. Columbus is around the Caribbean, and they are doing an awful lot of work in multiple countries from Miami, Dominican Republic, down to Venezuela, all back through Central America. I'll talk a little bit more about Gemini, Bermuda, and Hugo in a second. Very interesting. Looking ahead, as Samir mentioned, there's an awful lot of money goes into a cable system. Gemini Bermuda was a relay of an old Gemini system. And when I say old, it was laid and commissioned in 1998, and it was taken out of service in 2004 with a 25-year lifespan. The interesting thing is it was only 2.5 G capable for that distance across the Atlantic. But as Apollo came in, Hibernia came in, Tycho came in, the capacity and the cost per unit was dwarfed. And Gemini was a joint venture between MCI and Cable and Wireless. And basically it was retired, everything put into mothballs, the cable landing stations, and the cable was laying on the ocean. It was determined that with the optical amplification, it could be reused and just refitted at the cable station to put multiple 10Gs onto it. And basically the cable was, the southern leg of the cable from New Jersey to the UK was cut in the middle, and half from the UK was relayed to Guernsey and into France, into an existing landing station, and the other half from New Jersey, the existing landing station, was relayed down to Bermuda. And that cut the cost of laying a new cable, single-threaded cable to Bermuda in half, basically because there was no permitting, no trenching at either end, no cable building. There was only the re-equipping of the line terminating equipment and some of the power supplies. So it's become an interesting concept in the industry that you can actually, if the life of the cable is less than 10 years, you can actually pick it up and reuse it. There are new cables that are being deployed, and I'll talk about a few of those. System upgrades, as Samir mentioned, tranches of 16, 32 wavelengths at a time on multiple fiber pairs. And we're also, there's a 200 million investment in the intra-Asia cable, and this will give you a sort of guide on the route distance, the number of branching units, and what you get for your $200 million. So this is the intra-Asia cable. It runs from Singapore with branching unit for Vietnam, Hong Kong, Philippines, and this is where we're branching into the existing Tokyo Guam cable. So really it's from Singapore to somewhere in the midpoint between Tokyo and Guam with a new branching unit, and that is going to start on the 17th of June. The importance of this, as I step through, is when you look at it in perspective of the earthquakes. Most of the cable systems that are overlaid on it all ran through the Taiwan Straits. And what the cable is, the survey has done is take it as far away from that seismic activity as possible. So not only is it an important cable for Philippines and Vietnam, but it's also very important for as much diversity as possible from all the existing cable systems. The other one is Eurasia, which is coming in 2009, 9,000 kilometers, 1.28 terabits. Again, leveraging existing landing stations. IMEWE in 2009, very similar routing. This one is more of a consortia cable. The CECOM cable going up the east coast of Africa. Again, beyond the existing branching, there could be more branching units on that cable system, coming in the second half of 2009. The Trans-Pacific Express, which is China, Korea, Taiwan, and into Oregon, which should be ready for the Olympics. The Asia-America Gateway, multiple countries, coming in 2009. So there's as you can see, the trend here is from the early 2000s, where everybody shied away and moved away from investing in cable systems. With the capacity growth, there's a need to invest again. Hundreds of millions of dollars. Others are CFX-1, which is US, Jamaica, Colombia, which is going to dissect the Arcos ring, which spans all the way through as I mentioned earlier, Miami, Bahamas, Turks and Caicos, going all the way around the Eastern Caribbean, back through Central America, Panama, Guatemala. So this one dissects it and creates a couple of express routes for that system. Pipe, which is Australia, Papua New Guinea to Guam. Again, there's limited cable capacity out of Australia and New Zealand with Southern Cross and AGAC, Australia-Japan cable, so that's a big addition for Australia. Hugo, as I mentioned, UK Guernsey, France, which was a relay, and Gemini Bermuda, which was a relay of the Gemini cable system. The Europe-India gateway, as you can see, an awful lot going on through the Middle East and connecting India to Europe for the shortest possible route, also on to the US. Teams, the East African Marine System, which is, as Samir mentioned, in this instance, government funded and backed, which makes it ever more challenging, but between the UAE and Africa. Unity, which is a smaller consortia, a less traditional consortia, is connecting US to Japan with a ready for service date in 2010. There are a few others, but those are the major ones that are of primary interest on the main routes. And with that, thank you.
So at this point, we can take questions. You just come to the microphone and we will answer your questions. Everything clear.
Did I put you to sleep?
Anton Capella, 5 Nines Data. I'm curious about the power for undersea repeaters. Is that one single conductor between them and like a positive end in one continent, negative in the other? Or what's the makeup of that?
Do you want to talk about ground earths? Very rudimentary. Every system has a very significant earth at the beach manhole. It's quite. That's really the long and short of it. It's a very deep built ground earth, just like you would see at a data center.
I'm thinking though. I guess my question is, how do you get a voltage differential between the either end of that cable, or is the entire conductive path forward and back in the same sheath? I guess it wasn't clear in the slides there.
You actually have a power feed equipment coming on both ends, and you really you balance. Basically you have a voltage differential.
Sure.
At any, but you balance it so you come on each end because it's actually pretty long. That's what maybe this is your curiosity, right?
Yeah, exactly. I guess
right.
it wasn't obvious if you put positive and negative, if you will, coaxially or triaxially, whatever, down the cable, or if it was continentally differential.
So it's actually a differential. So you come from both ends and you actually balance the line.
Okay.
At some point in the cable.
That was the intuition, but it wasn't. Thank you.
Yeah.
That's amazing.
Sean Dallin. On the restoration and the protection alternatives you mentioned, what do you find is it usually the user's choice that the outages end up from cable problems end up resulting in services outages? It's the user's choice, or are there other issues resulting in the restoration protection not quite working?
If you look at an IPLC and the traditional method of restoration, most enterprise customers, for example, a bank, would expect automatic restoration with SDM1 and above type services. That's almost a given. With some of the slower speeds, they would expect the carrier of choice to provide restoration for the service. And that would be the 1 to the 4 hour type of arrangement where it's already pre-organized and restored. When you get to the ISPs, the biggest question becomes latency. And restoration routes tend to be quite a lot longer than the initial route. So what my experience is that most ISPs will buy a point-to-point unprotected service and then buy another on a different route from another carrier and do their own load balancing, restoration, whichever term, and take account for their peak capacity and what they need to be running at any given time on a chosen route. So in that instance, they expect on occasion that the circuit will go down, but they prefer to determine their own backup route because they can then narrow down the latency differential between route A and route B. If we do it for them as a carrier, it could be, the differential latency is of our choosing, and that becomes difficult for the ISP to manage.
On the land-based systems, grooming is often an issue. The carriers will groom the circuits to different cables without telling the user a lot of times. On the undersea cables, just because there's fewer of them, is grooming less of a problem?
On the undersea cables, I think carriers that use one for end protection do have that issue of grooming to different cable systems. It's unusual if you prescribed a route for grooming to affect you. We certainly most of the unprotected wave sails are on a prescribed route, whether it's an STM16 unprotected or whether it's a 10G protected. They tend to be known exactly which route they're on, and unless there is a commercial arrangement that allows a one-off restoration for some work that's going on to move them onto a different segment or a different route, it is unusual for unprotected waves to move between cable systems.
Hi, Brian Dixon, affiliates, formerly with Teleglobe a long time ago. For the cable landing component, obviously there's trenching that goes in to get it up to the actual terrestrial facility. Is it reaching the point where there's enough new cables going in that for some terrestrial locations, putting in the equivalent of a large conduit for the shore landing would make sense? I mean, when you do terrestrial digs, typically they'll put in a large conduit and then pull fiber through it. Is that something that makes sense in a landing situation for undersea?
It has been done where multiple ducts are run from the beach landing to accommodate new cables coming into it. Yeah, that is part of the foresight that goes into it.
Interesting.
Each cable from the beach manhole, each cable system does have its own unique backhaul path, which is typically, some of the beach landings may be half a block in, and as we saw, Cancun got washed out, or they could be 3-4 miles inland, or even greater. But that conduit from the beach manhole to the landing station is typically a single route, completely independent of any onward backhaul terrestrial system to the major city pumps. It's completely independent because it is running power also, whereas typical fiber optics is not.
Completely unrelated question. What about the new technology coming down the pipe, 100 gig? Are you guys planning for that on the undersea systems?
I believe right now they're talking about 40 gig, right?
Well, 40 gig terrestrial is already in service, but I haven't seen any examples of 100 gig in the
You're
plan
talking
yet.
about single channel 100 gig?
Yes.
Yes.
Yeah, it's really in development right now. And I know, but in terrestrial they've done ultra long haul system at 40 gig. But again, remember when you apply them to undersea, you're talking about really providing the reliability and also the cost effectiveness. Because when you go the longer distances, you have some non-linearity and dispersion effect in the fiber that have to be mitigated. So it's a little bit more complicated.
Thanks.
Vikas, AOL. It appears to me that the repeater is a single point of failure. Is that true?
I'm sorry, Vikas, what was that?
It appears to me that the repeater is a single point of failure. Is that true?
In a linear segment, absolutely, yes, it is. And that, hence the very, very extremely high mean time between failure on repeaters. The example that I showed you, without touting somebody else's product, but they claim not to have ever had a repeater failure. And that's a Japanese company, NEC.
And just to complement this section, so so the cable failure will take out the repeater, obviously, right? I mean, when you have the cable cut. Within the repeater, you have redundancies. Not only the quality and reliability of the components that go in it, but the actual design. Let's say if an amplifier fails, you have some redundant paths within the repeater.
Okay, all right, thanks.
Hi, Tony Tauber, Comcast. Doesn't need to be a long answer because I know it's just about to be break, but what about decommissioning? Do they ever, well, I'm sure things end their lifetime at some point, and do they ever decommission things earlier than their expected end because the technology is just not really worth the investment? It's gotten so slow and small capacity that it's really not even worth powering anymore.
Well, Gemini was a good example of that. It lived for 6 years on a planned life of 25, and it was both segment of it was both decommissioned and then reused. In terms of decommissioning and picking up the cable, I personally haven't seen any examples, but I know there are companies that will recover cable where absolutely necessary, and most of the contracts do have clauses that the cable has to be should be recovered at the cable operator's cost if directed by a governmental agency. But it's a little vague, and not too many of the cables have actually been picked up and recovered and recycled in the traditional sense of recycling.
Hi, Keith Wong, Connective. One question. It seemed like you showed a lot of new fiber builds. Can you put that in context with history? Is it a lot more significant now in 2008 to 2010? And second part to that, how does that change the pricing dynamics for transatlantic, transpacific?
Obviously, when you say in the context of the street, the investments that are going in?
No, in context of historical fiber builds. Because it just seems like there's a ton of new projects coming on board.
I can take that.
Go ahead.
There has been, there was a lot of fiber constructions in the early 90s,
Yep.
and it created what we call in the industry the fiber glut. There was an abundance of fiber everywhere. And then the dot-com boom happened and the bust happened, and a lot of carriers went bankrupt and cable operators went belly up. And that inventory of submarine systems stayed on. And it's only now, 6 years after, that we have finally exhausted the excess capacity in the submarine cables. And that is why you're seeing, this is quite unbelievable, like in the past 18 months or 12 months, there's been a lot of announcements, a lot of people wanting to buy cables or build cables, and the growth is truly in Asia, where the internet is finally booming, and this is what is driving the cable demand for new systems. So all these investments, if you look at the investment path, they all have either China or India as landing points, and those are the sought after routes. And you would be hard pressed right now to find some available capacity trans-Pacific. So all these new systems are coming on. So I think it's just natural economics of offer and demand. We've finally exhausted the inventory, which created rarity, and now it's spurred more projects to take on.
Okay, excellent. And does that mean pricing will begin to come down trans-Pacific? Thank you.
I'm sure it will.
I'm sure you can talk to your account managers.
Yeah, it's kind of ironic that you can get a transatlantic 10G for less than a DS3 from New York to Harrisburg.
So, are there any more questions? Did you finally learn what you wanted to learn about submarine systems? Thank you very much, Samia Bashoun and Paul Kerwin, for coming today. You have shown great examples, great pictures, and your explanations were very clear. Thank you so much.